The natural environmental systems that support our way of life are tremendously complex. They're composed of many physical, chemical, and ecological subsystems that are changing in time and interacting with each other.
When something goes awry in one subsystem, the impacts are felt in other parts. In seeking to understand how geoenvironmental systems will respond to stresses like population growth and a changing climate, scientists turn to computer simulations to address broad questions like, will permafrost in the Arctic become a net sink or source of carbon under a warming climate? What impact will a forest fire have on downstream water quality and availability? How effective is a remediation strategy in immobilizing contaminants at a waste site?
However, many of the modeling tools that we have traditionally been focused on one or two processes or subsystems and have great difficulty managing the vast complexity of natural environmental systems.
Environmental scientists need more holistic simulation tools that can incorporate a wider range of processes and their interplay.
AMANZI ATS was created to understand just these types of challenges and their impacts to society. AMANZI is water in Zulu, and ATS stands for the Advanced Terrestrial Simulator. Together, these form a powerful tool for environmental simulation.
AMANZI ATS was developed by a multi-lab partnership of experts at Los Alamos, Oak Ridge, Lawrence Berkeley, and Pacific Northwest National Laboratories. It is open source, open development software available for anyone to use and to contribute to.
It leverages cutting-edge software for mathematical functionality, so it's been built for machines ranging from laptops to supercomputers, including Summit. What makes AMANZI ATS so unique is its ability to scale the complexity up and down to meet the need. This allows researchers to really leverage this flexibility by changing the processes and understanding the uncertainty of the solution with respect to the processes being represented. Researchers can tailor their simulation to meet the problem at hand. As each problem gets changed, a new term gets added and that gets built into the dependency graph. The code builds this graph on the fly, and that allows us to be extremely flexible in how we set up and run our simulations.
Researchers in the US and Europe have been using AMANZI ATS to understand thermal hydrology of Arctic permafrost. Across the Arctic, permafrost contains vast amounts of organic carbon that could potentially thaw and be released to the atmosphere in a warming climate.
Fire plays a crucial role for the forested ecosystems of the US Southwest. Under a warmer, drier climate, we've seen both increased intensity and increased occurrence of wildfire. How and to what extent fires affect the watershed depends on a wide range of processes, from the fire severity itself to the vegetation and the local water conditions. We modeled individual storms, both before and after fire, to understand what the fire's impacts were for the streamflow. The fire resulted in both larger and faster flows, which have important implications for water managers.
Protecting the public's health by safely cleaning up sites contaminated during historical nuclear weapons production is an important part of the Department of Energy's mission. Researchers from Lawrence Berkeley National Laboratory and Los Alamos National Laboratory used AMANZI ATS to model the seepage of contaminants and the effect of remediation at the F-area storage basins at the Savannah River site. Having validated these simulations with site observations, AMANZI ATS is being used to explore the impact of future climate scenarios on the effectiveness of these sustainable remediation practices.
AMANZI ATS allows us to make sense of the complex interactions governing the environment and how these things change in a changing climate.
That powerful knowledge is key to mitigating those impacts and maintaining the delicate balance upon which these environmental systems thrive.